Yeah. So she has like a walk on her back, so she's like.
Even for the honor seat. It's kind of hard, it's just, but that's what, it's so hard, it's so easy. But then you leave at 1:30.
So today we're going to go over evaluating improper integral. So this is where we're taking the antiderivative. We could potentially have to go through use substitution, but it's just that what happens if the bounds are not real numbers? What if it's going from 0 to infinity? Are we still able to find an area even if that region is going out to infinity? Or if there's some asymptote involved, there are some times we're able to find an exact area. There are other times we're not, but we're going to have to be able to know how to evaluate those types of problems. So we're working on that today. Tomorrow is Euler's method, which is it's like linear approximation, but done over a series of steps. So it's a bunch of linear approximation over multiple points. But let me address tomorrow, because tomorrow we'll hear later today, I think around 1 o'clock, whether tomorrow is going to be a remote day or whether tomorrow will be a regular school day. If tomorrow is a remote day, I want us to stay on track with our calendar. So from 9:30 to 10:15, I'll have a team session. I'll send out a Teams link through Remind like 5 or 10 minutes before, and then you can join and we can just work through those 3 pages, pages 16 through 18. If for some reason you're not able to join, it's okay. I'll have that recorded. You can watch it and then you can work through those pages. But if it's a remote day, I do want to push the homework out one day. So I'll delay the homework, but I want to stay with the calendar. So if tomorrow's a remote day, then I'll be checking this homework on Monday, this homework on Tuesday, and everything gets pushed back. But the quiz is still going to stay. It's just that we have all these review days, so we can just still push out, stay with the calendar, but then push the homework assignments out one day. All right. Any questions with that potential adjustment for tomorrow? All right. Let's look at our notes. Page 9. So improper integrals are area integrals with infinite limits of integration or have an infinite discontinuity on the interval. So here are some examples. The integral from 1 to infinity, 1 over x dx is an improper integral. And then the integral from -1 to 1 of 1 over x dx is also an improper integral because there's a break in the graph. There's an asymptote that is interrupting our interval, and we have to address that issue. We can't just take the antiderivative and just go through natural log and plug an upper lower bound and just completely ignore that there is a asymptote that is interfering with our interval. So this is what we're going to do here. If we see a bound that is a asymptote or infinity, we want to adjust that bound with a constant or with a letter. So here it says if the function is continuous on the interval from a to infinity, then the integral from a to infinity is limit as b approaches infinity from a to b of f of x dx. So we're going to let a letter, it can be any letter, typically we choose either a or b to represent that infinity. And then once we go through our definite integral process, then we're going to push that b out to infinity. So that's usually the notation that we use. We use a placement for that infinity, and then we put a limit notation in front of it. Okay, so have you guys copy that down, and we'll work through example 1. All right, let's look at example 1. Find the improper integral from 1 to infinity of 1 over x to the 4th dx. Now we can obviously tell, well, first off, there is no other breaks in the graph, right? The only break in the graph is at 0. There's a vertical asymptote at 0, but our bound is from 1 to infinity, so our bound is not getting impacted by an unexpected asymptote. So we know that our graph is going to be continuous from 1 to infinity. It's just that we got to deal with the infinity here. That's not a real number, but we could still potentially find the area of something that goes out to infinity. So let's set it up this way here. Let's make this limit. I'll use b to represent that infinity there. So I'll do b approaching infinity, integral from 1 to b of 1 over x to the 4th. I'm just going to get that ready for power rule. So I'll bring that up as x to the negative 4 dx. We can go through power rule here. X to the negative 4 becomes x to the negative 3 over negative 3. I'm going to clean this up, and then I'm going to evaluate my bounds here. So I'm going to keep my limit notation here in front. So all this process should feel very familiar to you. You would do this process anyways if that upper bound was a real number. So now we just have to carry this limit notation with us. Upper bound first. Minus a negative 1 over 3. Right. Any questions so far? Now, let's just see if this will end up giving us a real number, or if this can end up giving us something that we can predict. So if we're pushing out b out to infinity, that's in the denominator, right? What's going to happen to this fraction if b keeps increasing? Smaller until it heads towards what? It's good. So this is predictable, right? This is headed towards 0. That's a real number, so that's fine. We can keep that. And the rest is also a real number. So 0 plus 1/3. This tells us that this does, we call this converging, because the area is getting closer. It's increasing, but there's a ceiling, and that ceiling is headed towards 1/3. So we can say that our area, if it goes out to infinity, our area is going to approach 1/3, or we can say the area is equal to 1/3.
How do you know that first fraction's approaching 0? I can't.
Right. So imagine this b is being pushed out to infinity, right? So imagine it was like 100. 1 over 100 is a small number, right?
imagine that B goes out to 1 million. 1 over a million is even smaller number.
Yeah.
1 over a billion is even smaller number. That number is getting smaller and smaller and smaller. We can predict that it's going to eventually head towards 0. Questions so far? I think sometimes students have this question of, wait, if it's going out to infinity and if the area keeps increasing, how come we're able to know what the area is? And the reason that we can know what the area is because it's increasing, but it's increasing with a ceiling that we can definitely predict. So imagine a number that was like 0.3, and then it goes to 0.33, and then it goes to 0.333. Right? Technically, it's increasing, but it's increasing in a way where we can definitely predict that, okay, it's headed towards 1/3. And that's how we know that there are times when even though something is infinitely increasing, there's an obvious ceiling, and we can predict that ceiling, and we know what that area is. But there are other times when there is no predictable ceiling. If there is no predictable ceiling, then we have to say, okay, there is no limit. It goes out to infinity. We call that a diverging series or a diverging graph. So we can say in this case, the area converges to 1/3. Now, I also want to show an example where the area does not converge. So if the limit exists, the improper integral is said to converge. If the limit does not exist, the integral is said to diverge. Give me a second here. All right, so let's see if we can approach this problem here. Again, this is going out from 1 to infinity. The graph looks the same, but you can already tell that it's closing in at a slower rate. So there's more gaps here, which could potentially produce an issue. But let's see if we can discover that. So here, we'll do limit as b approaches infinity. We have a rule for 1 over x, which is natural log. So we can evaluate that. Natural log absolute value of x, evaluate it between 1 and b. Keep that limit notation. Natural log absolute value of b minus natural log absolute value of 1. Now, anytime you see a b in the numerator, that's an indication that there's some potential issue along the way, because what happens if I were to replace b with infinity? Is this going to come out to be a number that we can predict? This is going to go to what? Infinity, right? Infinity minus 0 is still infinity. So that tells us that this, even though the graph is closing in, it's not closing in fast enough, and the accumulation of area is going to keep increasing without bound. So here we say that there is no area here. We say that the integral diverges. And I just wanted to kind of show, if I were to test a couple of numbers here, let's say I want to find the area from 1 to 10, I get 2.3. The area of that region from 1 to 100 is 4.6. The area from 1 to 1,000 is 6.9. You can tell that it's increasing, but it's increasing without bound, right? It's not a predictable, oh, there's a ceiling that is headed towards. It's just it's increasing without bound. We can see it in our evaluation as well. So we call these p integrals. This is where I have 1 over x to the p, and if that p value is greater than 1, we're going to have a converging, meaning that the graph is going to close in on the graph fast enough in order to bridge that gap to allow us to actually be able to approach a real number. But if my p value is less than or equal to 1, let's say it's like 1/2 or 1/3 or 0.1, then it's not closing in fast enough. It may look like this, where it's closing in, but the area is going to keep increasing without bound. We're going to see this in a lot more when we talk about convergence and divergence in our infinite series unit. But this is a bit of a preview as to these p series that we're going to see later on. Okay, next page, number 3. Remember that definite integral requires the interval to be finite, and the first theorem to require that the function is continuous on the interval. If the interval does not meet these requirements, we need to manipulate the problem. Another form of improper integral is from negative infinity to infinity. So if we see both the bounds being improper, then we have to find an anchor so we can kind of break it up into 2 parts where we have a bound that is clearly a constant. So if I see negative infinity to infinity, I need to find a convenient number in between and break it up. So typically we choose either 0 or 1. So we go from negative infinity to 0, evaluate that, and then we do a separate one from 0 to infinity. But sometimes it can be from 1 to infinity. It really depends on the problem. Typically we choose 0, but if 0 is an issue, then we choose 1. We just want to choose one that is easy to evaluate. That's really the goal. Okay, it's easiest to use 0 here for C. If either of these integrals diverge, then the whole thing diverges. So we're going to be evaluating them separately, and we're just trying to see, can we prove that both of these go to a real number? If one of them doesn't, then the whole thing is going to break down. Okay, so I'm going to write this as negative infinity to 0. And then separately from 0 to infinity. Okay, we'll evaluate them separately here. So here, I think I'm going to choose A to represent negative infinity, and then I'll choose B to represent positive infinity, and I'll do 2 limit statements. All right, let's do this first. The nice thing about e to the x is the antiderivative is e to the x. There's no need for u substitution here. So e to the x becomes e to the x. I'm going to evaluate my bounds from a to 0. So I get e to the 0 minus e to the a. Now, e to the 0 is safe. That's 1. But minus e to the a, sorry, I changed that to b here. That's the same thing as 1 minus e to the negative infinity. And if I clean that up, that ends up being 1 over e to infinity. Is this going to be a problem, or is this okay? It's okay, because 1 over e to infinity is going to be what? 0. So if you see infinity in the denominator, that's a good sign. That usually indicates that, okay, our fraction is getting smaller. It's going to converge. So this piece is okay. This equals to 1. But we need the other half to also converge if the full thing is going to converge. If the other half fails, then the whole thing is going to fail. Okay, let's look at what happens on the other end. This is also e to the x. This one is e to the b minus e to the 0. Now, in this case, e to the b, which is if b is pushed out to infinity, what's going to happen here? Infinity. So this is going to fail, right? This is going to equal infinity. So even though one converges, that's not good enough. I need both parts to converge. If anything diverges, if any portion diverges, the whole thing diverges. So we can just simply say that our answer diverges or equals to infinity.
Could you put the answer down?
Yes. All right, let's look at now. Let's look at some problems where, what if one of the bounds is sitting at an asymptote? All right. So I'm going to have you guys copy down these notes briefly before we look at our next set of examples. So let's say our function is continuous from a to b, but there happens to be an asymptote at b. So what we can say is we're going to go from a to t. If we want to use a different constant than t, that's fine. But t will be where we're approaching b from the left side of b. So we're talking about this region here. The asymptote is to the right of our graph. So we're approaching our asymptote from the left side of the graph. And then if our asymptote is on the lower bound, then we want to go from a to b with approaching a from the right side of a. So we want to approach the asymptote from the parts of the graph that we know exist. Okay, let's look at number 4. So if we look at the denominator is going to tell us where there's a potential issue with our function. So if I were to factor that denominator out, I'll get x times x plus 4. Whatever causes the denominator to be 0 is going to be a discontinuity, whether it's a hole or an asymptote. In this case, these are asymptotes here. So we know that there is a vertical asymptote at x equals 0 and at x equals -4. -4 is not going to impact our interval because we're going from 0 to 2, but 0 is definitely an issue, right? 0 is an asymptote, but 0 is showing up as our bound. So we're going to have to approach that 0 from the right side of 0, right? Because our graph is between 0 and 2, so we want to start on the right side of 0 and head towards the asymptote. So let's set up our limit. I'm going to use t, but if you use a or b, that's fine. I'm going to get myself ready for u substitution. This will be a problem. Predictable u value here is that x squared plus 4x. So I'm going to evaluate that whole antiderivative, plug in my upper and lower bound, and then evaluate and see if I can convince myself whether this is going to give me a real number or it's going to give me infinity. So I'm going to go through my u substitution steps. I'm able to see a clear path to getting all my x to cancel out, because once I can factor that 2 out, I get 2 parentheses x plus 2, make that substitution with dx, and I can clearly see that I have a path towards getting my x to go away. I'm going to step to the side and just take my antiderivative here. There's a 1/2 that's going to come out in front. I'm going to get my variable ready for power rule. I need to bring that variable up to the top, right? Can't do power rule with my variable in the denominator. So the power rule, antiderivative using power rule, I get u to the 1/2 over 1/2. If I flip that 1/2, I get 2. 2 times 1/2 is 1. Replace the u back in terms of the original variable. And then evaluate my bounds between t and 2. Oh, sorry. My u value is x squared plus 4x. My bad. That should be x squared plus 4x in here. Okay, let me pause for a moment. Any questions so far? Up to this point, we're just kind of relying on previous knowledge in terms of use substitution to get up to the stage, right? Okay, upper bound first, followed by lower bound. So this gets us 4 plus 8, which is 12. 12 to the 1/2, the square root of 12. Minus. Now, whenever you see a one-sided limit, we always say that we ignore that one-sided limit notation, right? You always want to start off with your integer value or your real number, And then if you run into an issue, whether there's a vertical asymptote or whatnot, then you can worry about decimals. But we never want to use decimals to begin our process, right? We always want to start off, can I just do a substitution, evaluating that limit, and see if I can convince myself it's a real number. So if I were to plug 0 in, am I going to get a real number? Yes. So we're safe, right? There's no need to do anything else. That notation is there to indicate that we're approaching 0 from the right side because our graph is to the right of the asymptote, and then our graph is going to have to move towards the asymptote from the right side since there's nothing on the left side and our bound is not on the left side of the asymptote. So this does converge because root 12 minus 0 is a real number. So our area, even though there's an asymptote in the way, we're actually able to arrive at an area of root 12. Okay, questions? I'm sorry?
2 root 3 is also acceptable.
That's right. Yep. All right, number 5. Okay, this looks like a harmless problem. Looks straightforward. 1 over x is natural log of x. Plug in my upper and lower bound, and I have my answer. But what's hiding here? What's making this? Yeah, that there's a vertical asymptote that is getting in the way. There's a discontinuity that is hiding in between our interval. And I just want to kind of point out that, if you saw this on the AP exam, it's understandable if you miss this, right? It's just so hard to think about, oh, there's a vertical asymptote. I mean, you'll probably be expecting it on the quiz since we're looking at a very focused problems, and you're going to be expecting it. But so I guess that's the bad news is that when you're looking at all these problems on the AP exam and you have limited time and you see this problem, you're not going to think it's hard. It's going to be hard for you to think, oh wait, there's a discontinuity. I have to think about breaking it down. But at the same time, it doesn't always appear on the AP exam. So just be aware that if you miss a problem like this on the AP exam, it's understandable since you have so many problems. It's hard to think about, oh, there's a discontinuity that is impacting my problem. But that's what needs to be done is we have to split this up into 2 separate problems from -1 to the asymptote and then from the asymptote to 1 and see if we're able to convince ourselves what our limit is going to be. So and I'm going to adjust the 0 with t variables and then with the proper limits on both sides of that 1 over x. So this side is to the left of the asymptote. So we're going to approach 0 from the left side of 0, from -1 to 0. And this one, we're approaching, the integral is from 0 to 1. The asymptote is at 0. So we're going to approach 0 from the right side. We're going to start at the point to the right of 0 and then head towards the asymptote. 1 over x is nice in the sense that the integral rule is just natural log. There's no need for use substitution. So I'll just finish off the rest here. Let's see. Okay, think about, okay, so first off, this is what natural log graph looks like. I just want to just kind of give us some perspective here. So imagine us plugging in values getting closer towards 0. So let's say I plugged in 0.1, then 0.01, then 0.0001. What's going to happen to this value here? Natural log of t is going to become what? It's good. Well, what's going to happen? Natural log of 0.0001, this number is going to get, yeah, towards a real number or negative infinity, right? So you have a negative infinity here. You have a negative infinity here as well. It doesn't matter if one of them diverges, the other one will. The whole thing will diverge. So this will diverge. All right, just want to kind of. Let me just do this example here. Imagine you plug in natural log of 0.1 versus natural log of 0.001 versus natural log of 0.00001. Right. Definitely not headed towards 0. It's headed towards negative infinity. As we get closer towards 0, that y value is headed towards negative infinity. So that's going to cause us to diverge. Okay, page 11. Number 1 is pretty straightforward. We can just set up using power rule, plug in our upper and lower bounds, and then have b approaching infinity. Okay, try number 1. Let's see if we can get through 1 and 2, and then we can stop.
we should be able to convince ourselves that number one will converge. Since my b that's approaching infinity is going to be in the denominator, so that's going to, that fraction will get smaller and smaller. So 0 plus 1 is 1. For number two, we have improper integral with one of the bounds being infinity, but we have to think about a process to take the antiderivative there. So if you look at how number two is set up, that looks like a good candidate for a partial fraction, right? Because my denominator has a higher degree than my numerator, and also my denominator can be factored into binomial expression or a pair of binomial expressions. So after we split them up into our partial fraction, we can take the antiderivative, and then we can work on evaluating the bounds. Oh, there's something a little different about number two. I think it's good for us to go through this one. So I want to break that 2 over x plus 3, x plus 1 into the sum of two separate fractions. I want an a over x plus 3 and I want a b over x plus 1 because I want to solve an easier integral problem than one messy one. But to find a and b, I'm going to go through my cover-up method. So my factor here is -3. I'll cover up the x plus 3 and replace all the x's in the numerator and denominator. So when you make your substitution, make sure you include the numerator in your conclusion. So I have 2 over -2, which is -1. So my a value is -1. Find my b value. My x plus 1's factor is x equals -1. Cover up the x plus 1. Replace the remaining x's with -1. 2 over 2 is 1. So my a is -1 and my b is 1. Now that we have that, our antiderivative should be easier to manage because we're just looking at natural log, right? So -1 natural log absolute value of x plus 3 plus natural log of x plus 1. Evaluated between 1 and b. 0 and b. Let me talk about this process here because if you were to plug b in, you may be thinking, wait a second, this is giving me infinity, and this is also giving me infinity. How do I resolve this? So the way we work around, we have to be careful of these types of problems. So let me rearrange this a little bit. I'm going to put this term first. Okay. And then b is approaching infinity, right? So if you're looking at this going infinity minus infinity, how do I resolve this? The strategy here is we want to take advantage of these log properties, right? What log property can I do to clean this up? Motion property, right? So now this is natural log of x plus 1 minus or divided by x plus 3. And once we have it in this form, now we between 0 and b. So once we have it in this form, we can, and B is approaching infinity, we can actually think of this as horizontal asymptotes, right? Because what's gonna happen if B is approaching infinity? What's gonna happen to this fraction? Ratio of the coefficients, right? So this ends up being 1, so this ends up giving me natural log of 1 minus natural log of 1/3. And we can have an answer of negative natural log of 1/3. And this feels weird initially because you're thinking, wait, this looks like a negative number, right? But actually, I can represent this 1/3 as what? 3 to the -1. Bring that -1 down in front, and I actually get natural log of 3. This actually ends up being a positive number, right? We should be getting if it converges, it should give us it should give us a positive number. So negative natural log 1/3, I think it's acceptable, but I just want to point out that this is actually a positive number, ends up being natural log of 3. So whenever you see infinity minus infinity and you don't know what to do with that, typically it's because we have to use log properties to clean it up to the point where we can make a better evaluation. Okay, let me talk about homework here. So homework will be your classwork pages, as well as page 46 and 49, which are your AP practice problems. If we have school tomorrow, then I'll be checking this tomorrow. If it's a virtual day tomorrow, then I'll be checking this on Monday. So Mr. Hoja has to cover another class, so I'll be with you this period. All right, come get the phones.
Yeah, you can bring it up maybe a little bit, but.
The reason why is because I'm ignoring that natural log and I'm just thinking about how would I do this? If I'm approaching infinity, I'm just looking at compared to degrees. The degrees are the same, so I get 1/1. So this actually is on, which means that I can solve this.
3.7 might be usually if you apply early though. What they do is they look at every applicant's GPA and they depiles their accept, defer, and reject piles. So to get to the accept pile, or actually they have a holistic pile, defer pile, and then reject pile. So what's the review?
How do you know? Where you can see?
Further review your application and then decide if they want to accept it or not. Right? So if, let's say you have 9 like I did, what that means, well, for this application.